In this Kinetic Art tutorial, I want to show you how you can model this rotating Kinetic Art in Grasshopper. You can see that I can rotate this, and by increasing the number slider, I can have this Kinetic Art rotation. This is going to be a long tutorial, so be sure to watch the video till the end because we're going to model all of these sections in Grasshopper, and as you can see, we can control anything. So if I increase this number, the handle is going to be bigger, and it's going to control that like this, and then again we can rotate it, or we can just control the length of the handle by going to here and increasing or decreasing this. And also we can control the width of this, and we can control the width of this mechanism places as we're controlling this. So let's just show you that we can increase the offset, increase the height. And so this tutorial is going to be a complete one of modeling this Kinetic Art in Grasshopper. And to get started, first of all, if you're new to our channel, welcome. Consider subscribing because we have weekly tutorials about parametric design. And also, if you want to learn a Grasshopper from scratch, we have a course. I'm going to put it up here so you can check it out, the lessons we are adding each week, and enroll in our course. So let's get started from scratch. And what we want to do is to study the mechanism in this video that I've shown you at the first of the tutorial. Okay, the most important part of this art, the kinetic art, is the rotation of this handle. The most important thing is to model this rotation. Let me just show you an example here with a simple handle like this. So first of all, I want to show you the mechanism and how the kinetic art operates. Okay, so if we just simplify this mechanism, you can see that we can rotate this. Let me just rotate it around the lines. So these lines are really easy to model. This is just a simple line, and then we can just use the polar array tool to make them, right? We have 6 of them here, and then we have to model this handle rotating. After that, we can just simply model the boxes which is attached to this handle, right, like this. And then we can also use these 6 lines to make an offset and produce the way they are moving inside that. So the most important part is the handle, and this is really a cool example of a kinetic art and the mechanism. And let me show you some pictures here. Okay, if you look at this picture, you can see that there is something, the most important thing about the geometry of this handle is, assume that we start with this one, okay? When the handle moves, these sections, which is like these 3 sections, they move in a complete linear transformation, right? So this one will move in this direction, this one will move in this direction, and this one is going to go into this rail and move in that direction. So if we connect this handle from this point to the second point and the third point, we will have a complete equilateral triangle. And why this is an equilateral triangle? Because when we rotate this and reach this place, which you can see that this line is going into the center of this intersection, again we have this equilateral triangle. You can see that the red line here will be red line here, and exactly we will have a complete equal length for the triangle, and that is because of the symmetry of the shape. The symmetry of this shape will give us no way other than an equilateral triangle. Okay, just take a look at this video. When we go forward and start from this place, I want to start from this section because it's really easy to understand. You can see that we have an equilateral triangle here, right, that we have to model. And look at the center of this, okay? So the center of this equilateral triangle is this point. If you look throughout this video, you can see that this point is moving in a circle. So basically this motion with the center of this one, the center of this equilateral triangle is moving around a circle. Just look at this video. I will show you how it's moving. Let's just get started like this. You can see this is the center of the equilateral triangle and it's moving in circles. So the most easy way of modeling this in Grasshopper is to use a complete circle, as you can see here, and use that. Okay, so now let me just turn on the equilateral triangle here. You can see it here. The center is like this, and what we have to do is to just draw a circle around the center of this and with the radius of like this. This is the starting point. The distance between this point and this, the first point we had here and the second point we had here, is always the same, right? So wherever we are moving the equilateral triangle center point on the circle, we have to find the location of this point, and we can do that by drawing a circle on here with the radius of this length. So if we just draw that, you can see that this second circle, let me turn off the first one, is going to intersect this line, and let me show you with the second, with the red, and the second line with this circle. So if we just rotate this, this circle is intersecting here with these 2 points. Again, when we move it forward, we have it like here and here, and that's the most important part. That's going to help us to find the body and model it in Grasshopper, and then we can use the next steps to find out how it's going to move. So let's get started from scratch. I had to explain these steps because this is going to help you understand why I am doing this in Grasshopper. So first of all, we have to draw a line and put a polar array on it. I'm going to draw a curve and use this line SDL. And give this a start. Let's just give this a point and set this. You can put it anywhere. I'm going to put it on 0 because that's going to make it easy. Okay. The direction is in the x direction, so I'm going to give this a unit x. That's in the x direction, and let's give this a length. So this is just you can see it here, and this is going to give us the array of these lines. So we can just say polar array. You can even find that in the transform section, and here we have the array, the polar array here, and we want to make an array of this line. The plane or the center of the array is the center of the starting lines, and the number we want is like 6, right? So I'm going to give this like a 6, and that's it. So that's how we make the rails, the base of that movement. And as I've explained, we have to draw a equilateral triangle here. A trick you can use is to go to the vector. This is going to be fast grid, and use this triangular grid to make that. The plane or the starting of this grid is going to be again the center, as you can see here. The number of the x and the y, I'm going to extract that, is going to be 1. So I'm going to just give this a 1. And the size is the size of this handle, okay? As you just, we had it here. This was the size of the handle. You can see that we can make this bigger or smaller. So what we have to do is to control this. And this is the size. I'm going to make it maybe between 1 and 20. Okay, so this is the size we can control. Why did we produce this equilateral triangle? Because we want to find the center of this and draw the circle, which is the motion of the handle. So we have to draw a circle from the centroid of here and with the radius of the center. To do that, we can simply just go to the curve and use this centroid polygon center to find the center. That's actually a center for the vertices, edges, and area, which in this example is the same. Now we have to draw the circle from the curve. The center is the center of the project, and the radius is basically the distance between this center and this center. So we can just type dist to find the distance. You can also find it in the vector section and in the point here, distance. So let's just find the distance between the center here and the center of the array. And we can give this to the radius. Okay, so now what we have to do is to rotate that handle on this circle. What I want to do is to simply go to the curve section and select this evaluate curve, give it here, reparameterize this in the right click because this is going to make it from 0 to 1. Remember this. And now we can give it a number slider between 0 and 1. So let's just give this number smaller than 1, and you can see that we can evaluate this circle from the start to the end. Let's just name this the T, and that is the most important parameter in this example. This is going to rotate and simulate that kinetic art mechanism. Okay, so now we can evaluate this circle. What we have to do, as I've explained before, we have to find these 2 points. So we can draw a circle which is from this point and with the radius of this, right? And we can draw that second circle there. What I want to do is to draw a circle. The plane of the circle is going to be this point. The radius is going to be the distance between this point and this vertices, and because this is an equilateral triangle, these lengths are all the same, right? Let me just show you with these lines. These are all the same, and we had that before by evaluating that and using distance. So we can just simply give that distance again to the radius. And when I rotate that, you can see that this circle is also rotating on the base circle, which we explained before. Okay, turn this off. Now what we have to do is to find the intersection between this circle and these 2 lines. This first line is going to be this one, and the second line is going to be this one. And you can simply see it here. This is one of the points, and this is one of the points. So it's basically going to be like this. That's the movement of how we can model this kinetic art mechanism. And to do that, I have to do a little bit of extracting these edges because these are separate from each other. So I'm going to join this one with this one to get a complete line. And you know that in the project, it's going to move in this rail. And also join this one with this one to produce one line, and this one with this one to produce this third line that we need. So I'm going to go to the sets and use the list item to extract it. So here we go, the list item. I'm going to use this one to extract all of those 6 lines and join them with this is going to be 0, 1, 2, 3, 4, and 5. So we have to join the 0 with 3, right? I'm going to go to the curve and select this, join curves. And let me just connect all of those possible curves. So this is 0, 1, 2, 3. One of them, the second, and the third. Okay. Now we have those lines separately. Okay. What we have to do is to find the intersection of this circle with one of those lines. Each of them are going to give us the results we need. So if I just bring this in and move this a little bit here, go to the intersection, we're going to use this intersection of curve to get the results. I'm going to use this curve, and remember we're going to intersect each of them with a circle. This is going to give us one of the results. The problem with these two series of points, which is relatively for the head of that handle. And let me show you here. It's basically like this. The handle. This is those 2 points we have to connect that with a line, right? The problem here is that because we are finding the intersection, it's always intersecting the center also, right? That is why we have two series of points. If I move the cursor here, you can see we have always two series of points to do that. I'm going to show you a trick you can use to extract the head of that line. Let me turn off that triangle off. Okay. So for these two series of points, what I usually do when I want to extract it, especially in the geometric field and the mechanisms, I go to the curve and, for example, want to draw a line between these two series of points. One of them has to be grafted. What happens now, it's going to actually find all of the solutions between these series of points together, because one of them is in groups and another one is not in a group, and it's going to multiply and give you four different outputs, right, like this one. So you can see we have two groups of two, and then we have to flatten this. So if you don't know about flatten and graph, you want to learn more about data trees in Grasshopper, you can watch this tutorial up here. Or if you want to even know more, you can enroll in our course. We have a complete series of lessons on data management, but you can also learn about flatten and graph from that free tutorial. Okay, for now, what's going to happen, we have four lines, and that is really cool. Exactly the edge of here, the size of that triangle we gave for 15, for example, is exactly also for this one, so it's 15. And if I just scroll here, you can see that one of those lines is what we need, which is 15, and it's going to change when we rotate that circle. So what we have to do is to say, go to the mathematics operators, and I usually use the similarity instead of equality, because somehow there is an error, or maybe just a slight of an error there. We can use that similarity and say find the length of this line. If you connect the line to the number, it's going to extract the length and compare it with this number we had here. So I'm going to just connect a number to this so you can see that I'm using it here, and that's going to give you a series of true and false. Let's zoom in, and there is only one true, which is the line we want. So we can use this logic. Again, you can learn the logics in our course, but for now we can use the dispatch to dispatch these lines based on the similarity. So if I just turn everything off and give a curve to one of these outputs, which is the list A true, that is exactly the head. Let me turn off the circle, and that is going to be amazing. You can see we actually simulated the mechanism here. That's it. And you can also give that more than one, because Grasshopper will think that the circle is also recursive. So if I give it a 3, it's going to also rotate all around. So let's turn off the triangle. And here we go. You can see that this is the rotation of the head. That is beautiful, and we have find the results easily. That's it. And we also had another intersection for here. Okay, now we have to also draw the handle line, which is basically this line coming from here and rotating. If I just rotate this a little bit like this, what we have to do is to connect, similar to this one, we have to connect the line, these points, to the center of the head, right? Because the center of the head is going to go to the handle. We have to find the center, going to the curve. The point on curve tool is going to extract the center, and then we can connect that line here. It's going to give you two lines, and obviously if we bring that back to the location of the equilateral triangle, let me just bring that a little bit back like this one. Assuming that we had here, the distance is, the right distance is going to be like this one, right? Distance between the center of this to the center of the point of the array, right? We have to also equally compare that like this one and dispatch it to find the correct handle. What we have to do is to find the distance for the, let me just turn this off. For the distance, actually, we can find the mid-center of that. We have to go to the curve, go to explode, pick up the segments, which is list item, the first one and the second one. Find the mid of that, so it's going to be the point on curve tool. And now find the distance, dist, distance between the point of the array and the point we had here, which is actually the correct answer. That's not going to change, it's just going to rotate, right? So again, what we have to do, let me just bring that number up here. Okay, so what we have to do is to find which one is correct. You can see that these numbers are really near to each other. For the part of the equality or similarity, what we have to do is to find the threshold, which is really important here, right? If I connect a panel to this similarity, and that is because it's really similar, you can see it's near that, and that is because we are rotating. Let me just rotate that a little bit forward so you can see it can go into other numbers. You can see that this is going to give you different numbers then. So if it's near that first position, we have to also fix that problem, right? Which is really near the exact line. I have to just put that back, which both of them was true. This is also a trick you have to be considering. Here you can see it's really near, so I have to decrease the threshold to a number smaller than 0.01, something like that, and that's going to give you the true false. So remember, if you're not getting results of this similarity, you have to consider changing the threshold, making it smaller. Let's just put that also right here, so it's going to get us give us better results. So here we have this head, and now we have to use this dispatching thing, dispatch those lines and get the true of this. Here we go. Now we can just turn everything off, turn on the polar array, turn on the head of the dispatch, and turn on the handle. Okay, so let's just rotate this to check the results, and you can see that it's always giving you the correct answer. So this is really beautiful, and we are getting the results. Okay, the next part is because we want to put that as a 3D result, we have to make this handle a little bit bigger and extend it. So what I want to do here is to extend these lines. We can say extend, exte, extend curve. You can also find that in the curve utility here as the extend curve tool. What we have to do is to extend both of these heads and the handle. The type is by default on line. You can see it's going to extend that by line. So now we can just give that a number to extend it at the both start or the end. For the head, we have to give it to the heads at the start and the end. For the handle, we just give it to the end or start, doesn't matter. Let's just check this out. One of them has to be 0, so I'm going to extract this and give this a 0. Okay, that was the start and the end, so I'm just going to flip that, give the end a 0, and give that a handle. That's it. So now we can control the extension of the handle, the extension of the head, and basically that is how we model the mechanism of this kinetic art. You can see that we can change the size here, and that is the rotation. That's it. So actually in this step we have done the most important parts. And now what we have to do to reach the final 3D results, as you can see here, is a trick that I'm going to use to produce these offsets, the boxes, and give this a little bit thickness. So for the arrays, what we have to do is to go here. This is the technique you can use to give that a thickness. First of all, I'm going to give a pipe to all of them and give a radius. So we can just change the radius here, right? And now what we have to do is really easy. We have to go to the intersection and combine them together. So it's going to be a solid union, unite them together. And remember to flatten this, so all of those pipes, if you don't flatten, you can see that they are not in groups, and the solid union is going to be run in each of these data, but when you flatten, all of them are going to be combined. And now what we have to do is to have an intersection this with the XY plane. So the intersection and the BREP plane is the best technique you can use. So remember, you can always use this pipe union and intersection to produce something like this. Okay. To give it a thickness, we have to offset these. You can find the offset in the curve and the utility right up here. And I usually connect the curve also to the plane, so it has the same plane. You can see when I don't connect it, sometimes some of them are inside, some of them are outside, but when you connect it to the plane, it's usually the best results. For the distance, I'm going to give it a -x and give it a number. That is the thickness of the solid we want. And then we have to just loft these together. So remember, we had these two series of curves. This is one of them. Okay. We have talked about this before. For lofting each of them together, and these are in groups. This has to also be in groups, so we have to graft it. Remember, when we have to combine two series of curves together, both of them have to be in groups. And let's just put them into one curve so you can see what I'm doing. You have to have, when you just put your cursor on the curve, you have to have groups of 2. So remember, if you don't get that, also trying simplifying that will help you to get rid of those zeros and put them both into group of 2. So that is the technique you have to use, and we're good to go. We can just extrude that and give it a Z direction and give it a thickness. Remember, you can change that and give it that thickness. Okay, that was the steps for the body of the rail. Now we have to give that head a little bit of thickness and bring it up. So I'm going to also use a pipe technique again. Give this a radius. Like that. For this one, because we want to have borders and not like this one, which is open, I'm going to use the caps flat, so it's going to be a solid. Then I'm going to go to intersection and solid union, make it 1. Remember, you have to flatten, so both of them have to be into one group and united. Then we have to find the intersection with the plane. That's it. You can see that. Now we can just connect the surface from the params menu to make it a closed surface. And let's just move it up before we make the surface. So I'm going to move it up in the Z direction. That's obvious. We have to have more Z direction movement than this Z we had here, right? We had this here. So I'm going to give that a number slider more than 2. Move that a little bit up. Make that a surface and extrude that in the Z direction. Maybe just 1.5 and turn everything off. Okay, that's the handle. So remember, you can also add the extension here, the extension here. You can make it more thickness if you want to, and that's going to help you to visualize it better. So this is going to show you the rotation. Okay, for the last part we have to, let's just turn this off. We have to show those boxes, as you can see in here. And what we can do is really easy. We have to find the plane of these lines, which this is the plane of this line, this is the plane of this line, and this is, for example, the plane of this line. So we have three lines here. We can go to the curve analyzers and use this horizontal frame. I'm going to connect the first, the second, and the third with the shift key. And remember, you have to reparameterize this and give the parameter to maybe 0. Okay, we have the plane here. Let's go here. And what I have to do is to move these planes. This plane is going to go to here, this plane is going to go to here, and this plane is going to go to, okay, just drawn that bad, here, right? So we have to move the origin of that plane to the boxes. What I want to do is to go to the vector and plane, use this plane origin. We have to change the origin. The origin was those points we had. So let's go to the lines before we extended that. Where is this? Line extensions. Okay, this was the line without extension. So I'm going to use this curve and use this one, endpoints, to get the start and the end. These are 2 points. Then we have to also get this one, which is point on curve for the not extended one. Remember, that was the handle. That's it. Okay. So I'm going to put all of them into one point. The start is going to be here, which was the first plane, with the shift key, the second, and that is the third. If I give that to the origin, you can see that we have fixed it. Remember, there is a problem here. We have groups, and this is not in groups, so I'm going to flatten this to put it into one situation. Now we have the planes of the boxes that we can simply go to the surface primitive and use this domain box to draw them. These are the box emerging. Okay. The domain of the X is in this direction. So what I want to do is to say go to the math and use this construct domain to make a complete minus to plus domain. It's like, if I give it a number, for example 12.5, it has to, and we want the width of those boxes to be 12.5, we have to say from minus 12.5, let me just type it here, minus the number divided by 2 to plus the number divided by 2, which is actually the number. That's it. So I have to just make this minus x divided by 2 to x divided by 2. That is exactly the length for the x. For the y, we can control, make that a little bit bigger. And then for the z, I'm going to give it a number slider because I want it to start from the ground. So it's 0, it's not minus, and we can give this a number slider. And bring it up to just show that it's just for the front. It's sticking to the handle, something like that, to visualize the results. That's it. So these are the boxes. Let's just turn off the plane. And that's how we can visualize the results. By finishing the example, we can see that we are rotating these boxes. And if we want a better more length for these boxes, what we can do is increase the size of this. Maybe that's for the triangle. Increase the lines length so we have bigger. Okay, rows. That's it. And then we can increase also the extension. Where was that extension here? Okay, that was the extension of the handle. Let's just increase that. And now we can just make those boxes a little bit bigger. Okay, perhaps they don't have to intersect. Let's check this out. You can see that they are not intersecting. And that's how it's going to rotate. That's it. For the end, you can also use the display custom preview to give them a color. For example, a color for this one, another color for the head. Let's just give that swatch. Give this a color, for example, and then another color for those rails we had. Whatever you want to do, and then you can see that we can have them in 3D, or you could just bake that. We have done this in this file, and for addition we have also used the brep edges to extract the edges and give them colors so you can understand exactly the colors. So that is the tutorial of how you can make this kinetic art in Grasshopper. That was a really long one, but I hope it's useful to understand how mechanisms works. And this is a really amazing mechanism. It's just rotating. The most important part was that that equilateral triangle, which is rotating around the circle, which helps us to find the location of the mechanism and just understand how this is rotating around. So another interesting thing I want to show you is that if we go to this line that we extended here at the bottom and connect a point on curve, I'll just show you, this is interesting for some people maybe, and put that at the end. If we track this, this is going to be an ellipse. So if I just go to the params menu, utility, and use this data recorder, so just give that data recorder to these points and rotate this, you can see that this is moving around an ellipse. That's it. That's also the location of the handle. It's moving around an ellipse. You can study how the ellipse is located. Basically, it has to be in a plane, maybe this plane. The focal points are going to be maybe more complicated to understand. So I didn't use that technique. I just used the rotating equilateral triangle around the circle to find the results. Okay, thanks for watching. Remember to like this video because it's going to help this channel grow. Subscribe, and see you next time.